So good morning. So we are going to discuss unit number 4, which is time varying electric and magnetic field. Before starting, let me understand that the syllabus for this unit number 4 is it contains Faraday's law. So you are very much thorough with the Faraday's law, but still we will understand what is Faraday's law. The second topic is we will define what is displacement current. So we know that there are currents, but still here in this course we will discuss about the displacement current. And after that we will run with Maxwell's equation. A very important equation. Maxwell's all 4 equations. Next is the important theorem. After knowing the Maxwell's equation, we will go into the power calculation by using pointing theorem. Pointing theorem, and here we will discuss the following topic along with the theorem. We will also discuss about pointing vector. In addition, we will understand what is the power flow in coaxial cable. And at the last we will study the wave equation, how the wave equation will be from Maxwell's equation. So these are the topics in unit number 4. Before going into the topic, let me understand unit number 1. So here in unit number 1, we discussed the static electric field. So here the electric field will be static such a way that there will be a stationary charge. So in unit number 2, we studied the same static electric field, and in unit number 3, we have studied static magnetic field. So here the important thing is the current is stationary, the stationary current. Specifically, we can also write static charge. So in unit number 1, 2, 3, we understand that the time is not an important factor. Whereas in unit number 4, we will take time into consideration. So time will be considered. So in unit number 4, which is dynamic field, dynamic EM fields. So this is because of time varying current. So this is a short summary, and let me discuss what is Faraday's law. If I take the Faraday's law, here we know that the induced EMF, the word induced EMF is very important, which is electromotive force. If I take a circuit, the flow of current will be happening. Whereas if I take one more circuit, because of this current, there will be a flux formation around the coil. So this flux will cut the secondary terminal so that it will produce some current. The corresponding voltage is known as induced voltage, so which is induced EMF. So we are relating that EMF here. So here that VMF is equal to negative rate of change of flux for single turn. Secondly, If there are n number of turns, then I can define V EMF is equal to minus n d phi by dt. So for n turns. So this is a Faraday's law, and this negative sign will indicate the direction of EMF, direction of electromotive force, which will be always opposing. This is because of Lenz's law. So that is about the Faraday's law. So the electromotive force is equal to negative rate of change of flux, and the unit for this one is voltages. So this is a Faraday's law. Next thing is displacement current. Let us consider a circuit which is containing resistor and capacitor. So here we are applying the potential, resistor is here, capacitor, and the capacitor is filled with dielectric material. Let I be the current flowing inside the resistor is IC, and here it is ID. So IC is a here IC is a current through resistor, and which is nothing but conduction current. So we can able to understand that the current, whenever it is flowing through a conductor and resistor, the current will be conduction current. Whereas if the current flowing inside a dielectric or a capacitor, then that current is called as displacement current. In other words, the conduction current is a one which will because of actual motion of charge, and the displacement current is a one which is a displacement of the charge. If I take a capacitor, if I give the voltage across here, so we can understand that the voltage will be stored, the positive charge will be stored on the plate, and the negative charge will be stored on the bottom of the plate. So therefore there will be no continuous current flow. But when I disconnect this source, and if I connect a load, then I can understand that the charges will displace again. So with this movement we can have a closed circuit, and this kind of current is called displacement current. And if this current is taken per unit area, then that is called conduction current density. Again, if this current, the displacement current, is taken for per unit area, then that is called displacement current density. So again, if I take the resistor, so resistor, the current across the resistor is IC, which is defined by V by R. IC is equal to V by R, universal law. And if I take the resistance, so resistance can be defined as resistivity into length by area. And if I take area topward, it will become voltage area sigma. This sigma is called conductivity. So conductivity sigma is nothing but 1 by rho, and therefore V A sigma by length. So we can able to understand voltage per length is nothing but electric field intensity. So E A sigma. So this is your conduction current. So the conduction current is equal to E A sigma. If I want to find the conduction current density JC, that is given by IC by A. So if I take A outside, it will become sigma into E. So which is nothing but conduction current density, and the unit is ampere per meter square. So in normal sense, we will define conduction current density as conduction current per unit area, also sigma into E. So which is nothing but ampere per meter square. For the second case, current flowing through a capacitor or a dielectric. For such a case, I know the current ID is equal to dq by dt, general equation, charge per unit area. If I want to replace the charge by a capacitor, I know the well-known equation, capacitance is equal to q by v, and q is equal to c into v. So I can write dcv by dt. Since we have considered a parallel plate capacitor, the C is a constant which will become C outside. So which is epsilon A by D into dV by dt. Further simplification, epsilon A by D, I can write V as in place of E into D. This is differential D, and this is distance between the plates by dt. It is constant. It is taken outside, and therefore this D will get cancelled. So we will have dE by dt. If I take epsilon inside, it will become A into dd by dt. So this is your displacement current. If I want to find the displacement current density, I can put JD. JD is equal to ID by A. So per unit area A is equal to, if I take area outside, it will become dd by dt. Still I can write it as dou d by dou t. We can understand this is a full derivation, the derivative function, and this is a partial derivation. We know that the derivative is because of time. If it is x, y, z, then the partial derivative and the d derivative are different. Since there are only one variable, dou by dou t and d by dt will have same significance meaning, and therefore jd is equal to dd by dt. So which is ampere per meter square. So that is your displacement current density. So if I want to take the ratio, you will find JC by JD is equal to sigma by omega epsilon. So this is an important ratio. So if I take E vector, E is equal to some value, and here also there is E value. If I take E and differentiate, and if I take the ratio, you will get sigma by omega epsilon. So this will signifies when sigma by omega epsilon is very greater than 1, then the medium is a good conductor. If the sigma by omega epsilon, the ratio is less than very less than 1, so JC is greater in this equation, and this equation JD is greater, and it is nothing but a good dielectric. So this is a very important significance of this particular equation. The ratio is sigma by omega epsilon. If I take the correct indication, you will find there will be a J here, minus J will be here. So if I take the modulus, this will become sigma by omega epsilon. Since there is a J, the JC and JD will be always out of phase. If I want to specific, it is 90° out of phase. So J implies 90° and it is 90° out of phase. So that is about your displacement current and displacement current density. Next topic is Maxwell's equation. So very important equation, Maxwell's equation. So initially we are going to frame a first equation with help of Ampere's law. So it is a Maxwell's first equation with help of Ampere's law. This first indicates just for a number. It is not Maxwell's first equation. It is a Maxwell's equation using Ampere's law. So what is Ampere's law? So it is nothing but del cross H is equal to J. So this is Ampere's law. But here the J, whatever we are saying is conduction current alone. So we can able to understand there will be a current because of displacement current. So in order to add the displacement current, Maxwell introduced JD term, which is nothing but displacement current density. So therefore the current is total current for a conductor as well as dielectric, and therefore it will frame a complete equation, and this is your Maxwell's equation. To be specific, let me start with Ampere's law. What is Ampere's law? Integral H dot dl is equal to I enclosed. This is a Maxwell Ampere's law equation. If I can write a current value, I is equal to, we know that I is equal to, I is in terms of ampere. Ampere is equal to double integral J. J is current density ampere per meter square into ds. This is a known equation from unit number 2 or 3. Next thing is, if I compare these two equations, I can get integral, line integral h vector dot dl vector is equal to double integral, surface integral j vector dot ds vector. So here Ampere's contributed both conduction current and displacement current, and hence we can write double integral jc plus jd into ds. Still we can write integral L h vector dot dl vector is equal to double integral, in place of jc we obtain jc is equal to sigma into e, so sigma e plus jd. What is jd? Dou d by dou t, so dou d by dou t into ds. So this is your Maxwell's equation using Ampere's law. So Maxwell's equation using Ampere's law, which states that it is nothing but MMF, magnetomotive force. So what is the unit of H? Ampere per meter. DL is nothing but meter, so it will become current. So current can be written as magnetomotive force, which is equal to sum of current densities. So sum of conduction current density and displacement current density. Again, so it is an integral form. I can get a differential form by taking Stokes theorem. We know that it is a line integral and this is a surface integral. Since it is a line and surface, we can convert a line to surface with help of Stokes theorem. Using Stokes theorem for LHS alone, if I do that, I will get double integral S. So the Stokes theorem says that integral H dot dl is equal to del cross H into ds is equal to double integral S sigma e plus dou d by dou t into ds. Equating LHS and RHS, you will find double integral ds. So therefore, equating, I will get the equation as del cross H vector is equal to sigma e vector plus dou d by dou t vector, and this is your Maxwell's equation using Ampere's circuital law in point form or differential form. So this is the equation. So these are the two equations, which is nothing but Maxwell's first equation, and second one is Maxwell's second equation. So using Faraday's law. So we can able to understand that the Faraday's law is stated as, so here integral E dot dl is equal to minus dou phi by dou t. So we know that actually it is VEMF. So electromotive force is equal to, voltage is nothing but force. Electromotive force is equal to minus d phi by dt. And we can understand V is equal to, from the unit number 1, V is equal to minus integral. This minus is already obtained here. So it is integral E vector dot dl vector. So equation number 1 and this is equation number 2. From 1 and 2, I can write integral E dot dl, which is a closed line integral, is equal to minus dou by dou t phi. So this is one more equation. With this equation, I can replace pi is equal to, we know pi is equal to, what is pi? It is magnetic flux or electric flux, magnetic flux. So in this case, it is integral E dot dl vector is equal to minus dou by dou t Pi can be replaced as double integral surface uh, B vector dot ds vector. We know that pi is equal to, what is pi? It is Weber. Weber is equal to integral B vector, Weber per meter square into ds. So replacing that, you will get an equation, and this equation is called Maxwell's equation using Faraday's law in integral form. Similarly, if I want to get this point form, I have to apply the Stokes theorem. So Stokes theorem is given as line integral will become surface integral. Stokes theorem is operated in curl law, and therefore it will become del cross E vector dot dl vector ds vector is equal to minus dou by dou t double integral b vector dot ds. If I equate LHS and RHS side, I will find there is a double integral. There is a double integral with reference to ds, and here also ds vector. Both are ds vector, and therefore equating, I will get del cross E vector is equal to minus dou by dou t b vector, and this is your Maxwell's equation using Faraday's law in point form. So this is your second law, and still I can do two more equations based on Gauss law. So first thing is electric Gauss law. So Gauss law for electrostatics, electric field. So in this condition, I know that the Gauss law is defined as double integral d dot ds is equal to q enclosed. So here it is a surface and a closed integral. The closed integral is equal to q enclosed. For this equation, the definition, the statement is, it is EMF, electromotive force. E is volt per meter, dl is meter, it will become EMF. So the total electromotive force is equal to negative rate of change of magnetic flux. Negative rate of change of magnetic flux density. And here, coming back to Gauss law, double integral d dot ds is equal to q enclosed. Equation number 1. Still we can write this I is equal to q. That is one more Gauss law equation. But for this Maxwell's equation, this is very, very important equation. So with this equation, I can claim q is equal to, in terms of q is equal to, so triple integral rho v. So q is a coulomb, so 1 coulomb, and here it is coulomb per meter cube, which is into dv. So this is scalar, this is scalar, this is scalar. If I equate this equation number 1 and 2, I can write double integral d vector dot ds vector is equal to triple open volume rho v dv. So this is your Maxwell's equation using Gauss law in integral form, and this is called total displacement flux. So therefore the total displacement flux is equal to charge density, volume charge density is the theorem. So Maxwell's third law states that total displacement flux is equal to volume charge density. So this is a one form. If I want to get a point form, I have to apply. So here it is surface and here it is volume. This surface should be converted to volume. Therefore, it is triple integral applying divergence theorem. Triple integral, it will become divergence will be operated on divergence law. So it is del dot d vector dv is equal to triple integral rho v dv. Equating both side, I will get del dot d is equal to del dot d vector is equal to rho v, which is again a Maxwell's third equation using Gauss law in point form. And finally, the fourth law, which is Gauss law, Maxwell's equation using Gauss law for magnetic field. We can understand that if in the case of electric field, if I have a charge, it will have electric field in all the possible directions. But as per the universe, if there is a universe, when there is a north pole here, there will be a south pole. So without this north pole and south pole, the universe does not exist. The meaning is, if there is no one monopole condition, if there is a north pole alone, it does not exist. And therefore, with that basic sense, we are writing the monopole does not exist. With this simple logic, we can write double integral b dot ds vector is equal to 0. So this is the integral form, and we also know that if I take divergence for magnetic field, divergence, so it is a magnetic field. Magnetic field is curl in nature. If I apply the divergence for curl rotating field, it will be always 0 as per unit number 1. Del dot b is equal to 0, and del dot b is equal to 0, which is your second equation, and this is the first equation. It is called integral form equation, and this is called differential form or point form equation. So there is no proper derivation. With help of universal fact, we are writing double integral b dot ds is equal to 0, and if I apply divergence theorem here, still I can apply divergence theorem here. The surface will be converted to volume. Del dot b ds is equal to 0. So equating del dot b is equal to 0. So both are correct. So therefore it is a Maxwell's fourth equation. So Maxwell's fourth equation using Gauss law for magnetic field. As a summary, we have four important laws. The first law is from Ampere's circuital law. So the equation is integral h dot dl is equal to double integral sigma e plus dou d by dou t into ds. And along with that, one more equation is del cross h is equal to jc plus jd, which is nothing but sigma e plus dou d by dou t. So this is the first law. Second law, Faraday's law. So from the Faraday's law, we can write integral E dot dl is equal to double integral minus dou b vector by dou t into ds vector. Along with that, I can write del cross E is equal to minus dou b vector by dou t vector. So this is the second law equation. And third law, using Gauss law, generalized Gauss law is for electric field, which is double integral d dot ds vector is equal to triple integral rho v dv, both are scalars, and del dot d vector is equal to rho v, volume charge density. And using Gauss law for magnetic field, I can write double integral v dot ds vector is equal to 0, otherwise del dot b is equal to 0. So this is Maxwell's second equation. So this is a generalized form, whereas complete field equations with a reference to time constant and which is dynamically varying. If I take the first equation, this side is magnetic field and this side is electric field. If I take the second equation, this side is electric field and this side is magnetic field. Therefore, I can conclude that if the current is time varying current or oscillating current, if the current is time varying current, if there is a stationary current, it will contribute only magnetic field. If there is a static charge, it will contribute only electrostatics. That is, if there is a stationary charge, there will be electric field, but we can't able to assure the magnetic field. If I take the stationary current, movement of charge is nothing but stationary current, there will be a magnetic field, but I can't able to assure electric field. But in the case of time varying current, whenever there is a electric field, there will be a magnetic field. So both will be present if the current is time varying current. So that is why we are writing dou by dou t, dou by dou t. If there is a time varying parameter involved, we can conclude there will be electric field and there will be a magnetic field. If I take this two field, it will never contribute for radiation or the wave phenomenon. Whereas if I take this particular field, since there is an electric field and magnetic field, it will contribute for wave propagation. So this is a very, very important equation in which the time varying current will have electric field and also the time varying magnetic field. And that is the conclusion. Whenever there is electric field, there is a magnetic field. Whenever there is a magnetic field, there will be a electric field, and that is the conclusion from Maxwell's equation. So Maxwell derived or explained all the equation. He considered all the equation like Ampere's law, Faraday's law, and Gauss law. He consolidated a beautiful time varying equation, and these are the Maxwell's equations. So next topic is pointing theorem. Let us before understanding the pointing theorem, let us understand some important facts. If I take E, E is nothing but volt per meter, electric field intensity in terms of volt per meter. If I take H, H is nothing but amp per meter. And in the circuit theory, we are known, we can able to understand V is a voltage, I is nothing but current. If I want to find the power, I will write V is equal to V into I. This is called instantaneous power. If I want to find the mean power, root mean square power, it is V I by 2, which is nothing but V by root 2, I by root 2, which will contribute V I by 2. This is a power. So on the unit here it is watts. But if I take this field mechanism or wave mechanism, I can say that it is electric field and this is magnetic field. And if I want to find the power is E vector, the point, it is nothing but P vector is equal to E vector cross H vector. Since it is a vector kind of thing, we always use a multiplication as cross product. So the power is equal to electric field cross H field, and therefore the unit here it is volt per meter into amp per meter. So here volt amp is nothing but watts per meter square. Therefore this P can be redefined as it is a power, or it is so called as power density, since it is involving meter square concept. So it is called power density, and this power can be also call it as pointing power, which is nothing but pointing vector. So if the electric field is located or it is traveling in x direction, assume it is traveling in x direction. And as a secondary case, if I take the magnetic field which is traveling in y direction, then we can understand it is E cross H. If I cross x with y, I will get the positive z direction. Therefore, the power will travel in z direction. So since there is a cross product, if I take one in one direction, the second in other direction, then the third power will be in z direction. It need not be the same. If E is in both x and y, if H is in y and z, and correspondingly by crossing that H vector plus y vector, cross y vector plus z vector, using determinants, I can evaluate the P vector direction. So if it is single direction, if it is x direction and it is y direction, I can get the power in z direction. If suppose when the x is containing both direction, y is containing both direction, if I make a cross with help of determinants, I will get some answer. That answer will provide in 2 direction or 3 direction. So depending upon the determinants, you will try and find the power direction. So the power will be in the third direction. So that's all about your pointing vector. So I defined pointing vector. In tomorrow's class, we will see what is pointing theorem and how the power flow in the coaxial cable And what is the difference between instantaneous Poynting vector, complex Poynting vector, and average Poynting vector? Thank you.
நான் மியூட்ல இருக்கேன்.